Have you ever wondered how we can harness the infinite power of the sun to meet our daily energy needs? Well, today we are delving into the world of solar panel energy, where sunlight is our ultimate source of clean and affordable energy. Let's take you to this enlightening journey of exploring the incredible potential of solar energy. Solar panel energy has substantial environmental advantages, such as lowering greenhouse gas emissions, minimizing air and water pollution, and conserving natural resources. Solar panels help to prevent climate change and provide a cleaner future for future generations by capturing the sun's clean, renewable energy. The Earth intercepts 173,000 terawatts of solar electricity. That's 10,000 times more electricity than the world's population consumes. So is it conceivable that the world could one day be fully dependent on solar energy? To find that out, we must first understand how solar panels transform solar energy into electrical energy. Solar panels work through using solar energy and converting it into other forms through a process known as the photovoltaic effect. The photovoltaic effect is fundamental to the energy generated by solar panels. When sunlight reaches the surface of a solar panel, electrons within the silicon atoms are energized. The energy received from sunlight allows electrons in silicon atoms to generate enough energy to break away from their atomic bonds. This electron release causes a charge imbalance within the solar cell, resulting in an overabundance of negatively charged electrons and positively charged holes, which are vacancies left by the freed electrons. Flow of electrons and electric current. The charge imbalance in the solar cell leads electrons to flow in a certain direction. This passage of electrons generates an electrical current, or the movement of electric charge. But how does this electric current convert into useful electricity for our homes and offices? Let's take the procedure step by step. Solar panels are made up of photovoltaic cells, which are the key components that convert sunlight into electricity. These cells are typically made of silicon, a semiconductor material with unique electrical properties. Each cell has numerous layers, including a p-type layer with an excess of positive charge and an n-type layer with an excess of negative charge, which are separated by a junction. When sunlight strikes a solar panel's surface, it transmits energy to the silicon atoms on it, causing electrons to be released from their atomic bonds. The doping process generates an electric field within the solar cell's semiconductor material. Doping is the technique of introducing impurities into a semiconductor material to create areas with surplus electrons, n-type, and regions with a lack of electrons, p-type, resulting in the formation of a p-n junction. The p-n junction within the solar cells generates an electric field as a result of these free electrons, which facilitates the movement of released electrons to the n-type layer, while positively charged holes migrate to the p-type layer. The electric field causes the passage of electrons and holes, which separates charges and creates a potential difference between the two portions of the solar cell. This potential difference, or voltage, enables electrons to flow, creating an electric current that may be utilized for a number of purposes. Metal contacts on the top and bottom layers of the solar cell capture the passage of electrons. These metal contacts operate as electrical terminals, collecting electrons and directing them into an external circuit for later usage. The photovoltaic effect causes the solar panels to generate direct currents, DC. Direct current is described as the transfer of electrical charge in a single direction, from negative to positive terminal. While direct current electricity is suitable for a variety of applications, the bulk of home appliances and the electrical grid use alternating current, AC. An inverter converts solar panel power into a form that is usable by household appliances and the electrical grid. An inverter is an electrical device that converts direct current to an alternating current. Rectification, filtering, and modulation are all phases of the conversion process that result in a sinusoidal AC waveform. Inverters convert direct current to alternating current, allowing solar panel electricity to be used successfully in homes, businesses, and the electric grid. Initially, the incoming DC current passes via a rectifier circuit, producing a pulsating DC waveform. The rectifier frequently uses diodes to allow current to flow in just one direction, successfully converting the negative half cycle of the AC waveform into positive DC voltage. The pulsating DC waveform is then routed via a filter circuit, which commonly includes capacitors and inductors. The filter smooths down the waveform, reducing ripples and harmonics in the output voltage. In the last stage, the filtered DC voltage is modulated to produce an AC waveform with varying voltages and frequencies. This modulation approach, known as pulse width modulation (PWM), alters the width of the pulses in the waveform to get the desired output characteristics. By adjusting the duty cycle of the PWM signal, the inverter may alter the amplitude and frequency of the output AC waveform to satisfy the demands of the electrical grid or connected loads. The resultant AC power, in the form of a sine wave, is sent to the inverter's output terminals. This alternating current electricity can be utilized to directly power domestic equipment or distributed to other customers via the electrical grid. The inverter transforms DC electricity to AC power, which may subsequently be used directly by household appliances. Alternating current energy is required for both domestic and business use, since it powers lights, refrigerators, air conditioners, TVs, and so on. Furthermore, extra AC power generated by solar panels may be sent back into the electrical grid. This grid-connected operation allows solar panel owners to manage their power usage and potentially earn money by selling excess electricity to the grid. Solar panel systems connected to the grid contribute to grid stability, energy security, and the transition to renewable energy. Inverters in grid-connected solar PV systems have synchronization mechanisms that ensure the AC output waveform is in sync with the grid's voltage and frequency. This synchronization mechanism, known as grid tie operation, allows the solar PV system to seamlessly inject excess electricity into the grid, while also receiving power from the grid when solar production is insufficient. Utility meters, also known as net meters or bidirectional meters, are used to monitor the flow of electricity between the solar panel system and the grid. These measures show the amount of power generated by the solar panels, the amount consumed by the home, and any excess electricity exported to the grid. Once the AC current from the solar panel is linked to the distribution panel, it is incorporated into the existing domestic wiring system. Solar-generated power may then be routed to lights, appliances, outlets, and other electrical loads around the home in the same way that grid-supplied electricity is. Circuit breakers are positioned in the distribution panel to prevent overloads and short circuits. A separate circuit breaker is frequently constructed for the solar panel system to isolate it from the rest of the electrical circuits and increase safety. Solar panels generate electricity, which may be used to power homes, businesses, and numerous electrical gadgets. Excess power created during periods of high sunshine can be stored in batteries and used later when sunlight is not available, or it can be exported to the grid if the system is grid connected. Battery storage systems provide increased energy independence and resilience, especially in off-grid or isolated places. Solar energy is now being used not only at domestic but also at industrial scale throughout the world as a cost-effective and dependable source of electricity. Industries are putting solar panels on rooftops, parking lots, and unused ground to generate power on site. Solar panels provide energy, which fuels a variety of industrial processes, such as machinery, equipment, lighting, and HVAC systems.